Welcome to Ling 360, Linguistics 360. This is speech processing. My name is Earl Brown. I'll be the instructor. And this the purpose of this video is to give you an overview of the course and some basic concepts around speech and sound files. Okay, so let's take a look at some slides here. If I go to there. So I'm going to use the course management system called Canvas, which is very much like Learning Suite. If you're not familiar with Canvas yet, it's pretty easy to use. I have the syllabus there, I have learning modules, and that's where you'll find homework, and you participate in discussion boards there. I run this class as a flipped class, meaning you watch videos like this, do some reading, exploring links that I present in my PowerPoint, and also this participate in a discussion boards before class. Those are due the minute before class starts. And then during class period, you actually work on a lab at your own pace and with me there to help out as needed. That's the way I run this course. And one of the objectives of this course is to get familiar with at least one programming language, perhaps try and pick up another one. And if you know Python, that's a great start. Python is used in many different human language processing applications. And also, you will likely learn one integrated development environment, which IDE for short is a way to write computer code that in an environment that allows you to run it and has some tools that help with writing code. And also we'll learn at least one web-based service for writing code, Google Colab. There are others out there, but I'll show you Google Colab. You'll learn toolkits and become familiar with corpus and language resources. And it is a class about speech. So, yeah, like I mentioned, you need to finish the preps, what I call preps, for each lab before the lab session. That includes the recorded lecture and any readings I link to or ask you to explore, websites or videos, and also to participate in class discussion boards on Canvas before class. So in class, like I mentioned, the majority of the class time is spent on working on a lab, like hands-on lab. And I often offer several options so students can choose which piece of software or which toolkit to work on for that given lab. And you generally have 1 week to turn the lab in after the class period that we start the lab or work on the lab. And just to point out, several students in the past in this class, their labs and their final projects have led to theses, master's theses, or publications, or conference presentations, or even internships. Just to be very upfront, students with the ability to process speech are marketable. And we go incrementally. We start small, become more and more complicated and complex over time. But that said, don't get behind. You cannot get behind. After a certain amount of days, you can't turn in labs. Anyway, so yeah. And the final coding programming project, you produce something cool with speech, around speech, that you could potentially show off to employers or graduate school admission committees or others. So let's real quick talk about what an integrated development environment is. You may know what these are already, but there are a lot of them, and it enables you to write code and to look at documentation about the functions and the programming language that you're using and to run it. There are a lot of them, and I have a link there on the second bullet to a Wikipedia article about many different IDEs. Okay, I'll let you explore that. And they're useful because they have intelligent coding assistance. They have smart completion, like it'll sense what you're trying to write and enable you to just push tab to accept the suggestion. And it can do syntax highlighting and error checking, all sorts of things that just a basic text editor cannot do. Okay. And also there are rich navigation capabilities. You can search for functions and files and classes, which are a type of computer code. And you can look at a project structure if you have a big project with different files interacting with each other. Some of the most popular ones, Visual Studio Code is a popular one. PyCharm is one specialized for Python. Spider, that third option there, is one specialized for kind of data science oriented Python code, and others. RStudio is the best one for, in my opinion, the best one for R if you're writing R code. Okay, web hosted services, like I mentioned, we'll look at Google Colab. I have a handful of what are called notebooks, Google Colab notebooks for you, but there are other web-based services, Amazon Web Services there, Microsoft Azure, and others there. And the cool thing about these services is that they offer access to larger amounts of RAM, as well as access to what are called GPUs, or graphical processing units, which make code go quicker than central processing units, or CPUs, which is what our laptops have and most computers that we use. So you can get access to that higher, strength processing ability. Okay, let's talk about language itself for a couple minutes here. Text versus spoken language. Spoken language is natural. Written is less natural, right? It's something we have to learn, and a lot of people don't learn, right? A substantial portion of humanity doesn't learn to read their native language, their native spoken language, right? Spoken language is much more pervasive than written language. If you just think about yesterday and how much you spoke or heard somebody speaking in comparison to how much you read or wrote yesterday, it's probably that you, it's very likely that you spoke and heard language much more than wrote and read language yesterday, right? And spoken language is much more universal. Everyone with, kind of normal cognitive ability learns to speak their native language, but not all learn to write, like I mentioned. And of the 7,000 plus languages in the world, many have not even been written down yet. Here is a link to ethnologue.com, that is. And you can take a look there if you want. I have a link on the PowerPoint, there are the slides here. Okay. Like I mentioned, a lot of people don't learn how to read. And women represent about 2/3 of all illiterate adults globally. So points to consider, ponder: how does technology help or hinder human-to-human communication? And is current technology equally developed between written versus spoken language? Okay, so what is speech processing? Well, it's the study of sound signals, of speech signals, right? And it's the study of processing methods for these signals. Okay, digital signal processing deals with phonetics, acoustic, as well as articulatory phonetics. Speech recognition, like taking speech and turning it into a transcript in written language, or speech synthesis, which is the reverse process, right? Taking written language and creating speech, like an artificial voice type of thing, like Alexa or Siri. There's a lot more to Alexa and Siri than just speech synthesis, but the voice you hear is synthesized speech, right? Neurocomputational processing, dialogue, and discourse, conversation. And applications can be like agents and chatbots and digital assistants, right? Like I just mentioned, Alexa and Siri and Hey Google, etc. Okay. Microsoft Academic as well as Google Scholar have kind of categories on their website dealing with technologies and conferences and institutions that deal with speech processing. Okay, so on the left-hand side, field of study, speech processing deals with computer science and speech recognition. These are all kind of related here. The second column, conferences. Let's take a quick look at some of these conferences. ICASP, Inner Speech. Let's take a look at those real quick. If I just simply Google ICASP, a recent ICASP here. It is the International Conference on Acoustics, Speech, and Signal Processing. Okay. And take a look at Inner Speech here, real quick. Interspeech, recent conference, or edition of that conference. It's Human and Humanizing Speech Technology, right? So there's yearly conferences around speech processing. There are a big list. Affiliations, these are kind of the institutions, many of which are universities, that are working in speech processing technologies. MIT, Carnegie Mellon, where one of our colleagues did his graduate work. University of Edinburgh, we've had a couple undergrads from BYU in the last 3 or 4 or 5 years go from our undergrad program to their master's program at the University of Edinburgh in Scotland to do their master's degree in speech processing. Very competitive program. Anyway, and then quite a few journals that deal with speech processing technology. You can find information on Microsoft Academic. Google Scholar has similar information on these fields and events and conferences and programs. Okay. Other valuable web resources. I have links here. You should take some time to look at some of these. This is the International Speech Communication Association. The Association for Computational Linguistics, ACL Anthology. You can look at events here. And over the past, several decades, has many over 80,000 papers right now, time of recording. Okay. And others. Wikipedia's, you can look at their processing, speech processing article there and look at, let me jump back over there real quick, and look at their references, see what references they have down here. Okay. And others. This is the Association for Artificial Intelligence. Is that what this is? Yeah, Association for the Advancement of Artificial Intelligence. You look at their conferences, all sorts of conferences and people and journals that deal with speech processing. The bottom two here, the Linguistic Data Consortium, is kind of a clearinghouse or a warehouse, digital warehouse, of all sorts of language corpora, not just speech, but they do have some speech corpora, many speech corpora that are available there. And it's taking a bit to load. Let me show you the ELRA, the European Language Resources Association, is another source for language data. Going back to LDC, which is taking a while to load here. This second from bottom one, Linguistic Data Consortium, is a consortium hosted at the University of Pennsylvania. And BYU has subscribed to their service over the past couple decades, and so we have access to a lot of their resources. So anyway, if you find something on their website that you like to use, you can ask me. If we already have access to it, we can get you that resource. So that means you should not directly buy. I would not recommend you buy the resources. They're very expensive, but because BYU is subscribed, we have access to a lot of resources there. Okay, let's talk about phonetics for a second. Phonetics, what is it? Well, it's the science of describing and inventorying the features and the structure of the basic sounds of speech in different languages. That's what phonetics is. There are two main branches of phonetics. Articulatory, which talks about the body parts, like how does the tongue move, what positions does the tongue have to be in for a certain sound to be produced, like, a T. In my variety of English is a dental, right? The tip of my tongue touches the back of my upper teeth, T, or even my alveolar ridge. And my velum closes the airway going out my nose, so it's not a nasal, it's just an oral sound. Anyway, that's articulatory phonetics. Acoustic phonetics deals with sound waves and their properties. And, on the bottom right of this slide, we see a waveform on the top, like the peaks and valleys here. We have a spectrogram here, the middle tier. We have a pitch track there on the bottom tier. So those are kind of the two main branches of phonetics. Articulatory, where you're looking at body parts and how they move and work together to create certain sounds. And then acoustic deals with like studying the sound waves themselves with software. And phonetic units of analysis, right? Obviously the individual sounds are segments, right? We can represent those like b, g, r, or y, like medallion, or these other sounds on the right here that I don't even know, that are in other languages that I don't know. Here's an interactive IPA chart, International Phonetic Alphabet chart. You can listen to certain sounds. Let's try this one.
Sha, asha,
Sha.
sha, asha.
Anyway, so that's, the phonetic analysis, unit of analysis is segments. Now you can group, sounds together into classes. We talk about vowels, we talk about consonants, and we talk about glides, which are kind of like halfway between a vowel and a consonant, right? And we talk about syllables, groupings of sound segments together. Articulation, we talk about the manner and place of articulation as well as the action of the vocal folds, whether it's voicing or not. Right, so we can talk about nasal sound, which causes some of the air or all the air to go out the nose rather than the mouth. Right, I'm stopping the airflow out of my mouth; it's coming out of my nose. Or or a back vowel like k or ga, etc. Voicing z, like zoo versus su. Zoo has a voice sibilant, whereas su has a voiceless sibilant. So. And then orthography is important to consider in speech processing because, as we know, there are varying levels of correlation between the way something is written down in graphemes or letters or characters, right, symbols, and how they're pronounced, right? So some languages have a pretty close connection between the way something is written and the way it's pronounced. Like Spanish, for example, has a pretty close connection between the way it's written and the way it's pronounced. There are some exceptions, but it's pretty darn close. Whereas English and French and Danish, pretty far. Like the connection is pretty far. And some languages, as we know, like Chinese, right, Mandarin Chinese, have logographs where it's representing a word or idea, or like hieroglyphs, right, represent like an idea and not representing sounds. So anyway, varying levels of correlation between pronunciation and writing. Let's see. Yeah. So the International Phonetic Alphabet, as you may or may not know, was created in order to try and represent the actual sounds of languages and not using the orthographic conventions of that language. And so each symbol represents one sound. So the point of it is to not have any ambiguity between what's written down and what is said. And this is used by linguists to represent sounds in speech. And there are hundreds of writing systems. There's over 1 million graphemes or different symbols. In English, we have 26, right? 26 letters. But if we add up all the different symbols and letters and logographs in the languages, it's a lot. And Unicode, the Unicode character encoding system was created, I think in about the 1980s, I think it was, to represent all the graphemes, to represent all the sounds, to represent all the graphemes, that is the letters or characters or symbols in all the languages, human languages that are known on a computer. So that's what Unicode's goal is. And so these days, almost everyone is using Unicode, UTF-8 specifically, to do their character encoding. And like I mentioned, that's what IPA is there. So other speech properties of speech that we'll deal with are suprasegmentals. So if the segments are the sounds themselves, supra are the features of language that are above those sounds or segments. Right, so like intonation, contours, loudness and tempo and rhythm, segment length and tone, in tonal languages that have rising or falling tones that change the feature, the meaning of words. Right, stress and rhythm, and vocal qualities like stress, emotion, deception, like the tone of a voice. Other things that influence speech, right, are breath and pauses, also disfluencies. If you actually record your speech and transcribe it sound for sound, you'll see like, whoa, I do a lot of like false starts, pausing. I'm doing it right now as I'm talking about it, thinking of it, repairs. Just as a funny little quick story here, I recently recorded my parents-in-law, and I had an automated speech recognition software transcribe it for me, and I was going through and fixing the transcription, just double checking and fixing problems here and there. Anyway, the microphone was far enough away that it wasn't the greatest quality. And looking at some of the errors that the ASR, automated speech recognition software, made was really funny, including like thinking that my mom-in-law swore during the interview, which she did not. Anyway, also gaze and gesture and blinking are important in speech. If somebody doesn't blink ever, which is probably not physiologically possible, it would be really weird. We need like pauses and blinks and, variation in gazes, eye gaze while we're talking. Here are some nifty phonetic websites that you should spend some time browsing around. We have the BBC Survey of English Dialects here. Take a look there. George Mason University Speech Accent Archive there. Here's an interesting video. It's a cineradiography. Cineradiography, if I'm pronouncing that correctly. It's an X-ray.
Her pair, her tear, her care, her pa.
Anyway, you can see the tongue moving and the vela moving and the jaw moving, obviously. Interesting video. Take some time there. Here's an interactive International Phonetic Alphabet chart that we saw a couple minutes ago. You can listen to sounds. Here's
sha, asha.
sha, sha. So anyway, take a look at those websites. They're nifty. So what is sound? Well, sound is simply variation in pressure through some medium, usually air, right? The vast majority of our time we're speaking through air. But you can't speak through liquid, like underwater, right? It sounds garbled because the medium is different, so it changes the sound in comparison to the way it sounds in air. You can talk through solids, like through bone, like cochlear implants for hearing aids for deaf people. It's putting vibrations into their bones so they can hear. But not in a vacuum. As far as we know, in outer space, if you were to talk, you wouldn't be heard because there's no vacuum through which the sound waves can travel. Okay? So sound involves production, transmission, reception, and there are, sources of sound, a diaphragm of a speaker, right? Or the human articulatory apparatus, that is the lungs, the throat, the mouth, and the nasal passage, the tongue, etc., teeth. All go into creating sound, or a tuning fork, or a reed instrument like a clarinet. Right, those all are sources of production. And the medium through which sound travels can change it, right? Reflect it, refract it, attenuate it, which means soften it or amplify it. And there are two fundamental basic elements of sound, which are pressure and time. So waves, like I said, sound waves are waves, like waves of an ocean going across oceans, right? And we can represent those waves different ways. We have a sine wave here in the top right, the first tier there, where you can do a sound or a square wave like that, or a triangle wave, or a sawtooth wave. And representing sound waves deals with physics and engineering and math, and you can think of it like a spring. Let's say we have a spring here like a slinky, a good old-fashioned slinky that you had as a kid, where you push one end, you can see the wave kind of traveling to the other end and maybe back. That's what sound waves are, just traveling through air. And we'll talk about different types or different properties of sound waves. Probably the most important one is the wavelength, and it is the distance or the amount of time that is between two peaks of a wave. So here we have a peak or a crest, and we have a trough or a valley here. And the wavelength is the distance or the amount of time it takes for one peak to be followed by the next peak. That's wavelength. Okay, so it's the distance between two identical points in consecutive waves. So up in the top right of the screen, we have three waves, and they're all the same amplitude, which amplitude is the distance between the origin or the midpoint between a peak and a valley. That's the origin, and the peak. So that's amplitude there. And we have the same amplitude because the height of these waves are the same, but they're different frequencies because there are increasingly more peaks within this time frame in the top right graphic of this slide right here. So we have 3 peaks here and 4 here and 7 or 8 there. So we have higher frequency as we get more peaks. So down here in the bottom left, we have hertz. Hertz is how many cycles, that is how many peaks, or from one peak to the next is a cycle. How many of those are there in 1 second? So here we have a 4 hertz sound, or not a sound, it's a wave. I don't think we would hear this. It's only 4 hertz. We have 4 cycles or 4 peaks in a second. So that's a 4 hertz wave. And here we have a 14 hertz wave because we have 14 cycles or 14 peaks in this second. And so hertz is the unit of measurement of frequency, or number of peaks in a time frame, in a second. Okay, good. And digital sampling. Well, so there are an infinite number of points on a wave. You could draw an infinite number of points, right? Theoretically. So we can't do that. That's not realistic. We can't take an infinite number of samples. And so we have to calculate how many samples are we going to take each second of a sound in order to represent what the sound is. And so let's say we have a sampling rate of a CD, compact disc quality. Remember what those are, the good old-fashioned days of CDs back in the, 90s when they came out, I think. I was probably in junior high. And they have 44,100 hertz. So there are 44,100 different samples in 1 second, is what that means there. And so it's taking a sample that frequently. Cassette tapes, the good old cassette tapes from the 80s, right, had 14,500 hertz. AM radio, if you have a car with AM radio still, shout out to you. They're sampled at 22,000, that K is 1,000, right, hertz. Telephones, the audio quality of telephones is so poor because it's only at 8,000 hertz, or 8 kilohertz. Human speech ranges between 300 and 3,400 hertz on average. So, like I said back here, I'm not sure we wouldn't hear those waves on the bottom left of this slide because they're too low for us to hear. Okay, so that's what digital sampling is. It's taking a sample where the sound, at a certain sample per second, a certain number of samples per second. Okay, so we're measuring acoustic pressure, and it's simply the sound waves that cause deviation of local ambient pressure. That's what sound waves are. And they're different units of measurement. A Newton is the force needed to accelerate 1 kilogram of mass at a rate of 1 meter per second squared, right? That's what a Newton is. Or a Pascal is kind of a calculation, mathematical calculation with Newton. This one down here, the third sub-bullet, decibel, is the one you probably heard the most with sound. It's a way of measuring the amount of pressure, the loudness of the sound. And so for air, we have 20 micropascals, the sound of a mosquito flying 3 meters away, right? And a Pascal is about 94 decibels. So here are different decibels. So fireworks are really loud, right? At 140 decibels. A jet engine is really loud as well, at 130 decibels on average, give or take. Right? A police siren, 120 decibels. Trombone, 110, etc. Hair dryers at 90 decibels. A conversation, moderate to quiet, is about 60 decibels. Faint or moderate rainfall is faint, about 50 decibels. Whispers at 30. And breathing's at about 10. So anyway, the decibel scale is used to measure the amount of pressure or the loudness of sound. And we humans can hear between about 20 hertz and 20,000 hertz. That's kind of our hearing range right in there. But there's obviously hearing loss. And so, sometimes older men, I'm just thinking of my father, for example, has hearing loss and he can't hear well overall, but especially in the higher frequency ranges. And I had my hearing tested a couple months ago, and I have a little bit of hearing loss in the highest ranges, in this range. You may have heard that elephants can hear below what we can hear. So they can hear below 20 hertz. So they can hear their companions talking to them farther away because lower frequency sounds travel on average farther than higher frequency sounds. Whereas bats can hear above what we can hear. They can hear above 20,000 hertz. So that's decibel scale. Real quick, let's talk about units of digital information. So computers think in zeros and ones. That's a bit, one binary digit. It's a bit. And those are combined, 8 bits are combined into a byte. And we often hear about units of measurement like kilobyte, like I have a file that's 200 kilobytes. Or I have an MP3 song on my phone that's 3 megabytes or whatever. Or I have a hard drive that's 500 gigabytes. Or you can go to Costco these days and get a 5 terabyte external hard drive for your computer. And these other ones we haven't quite seen much yet. You may have heard about it on some news article about some scientific something I heard that, like, what was it? The Julia programming language was used to analyze like petaflops of data of the sky. Anyway, these are larger and larger units of measurement of bytes. And these are processed, these are kind of combined into what are called processing words. And you have 32 bits or 64 bits. These days, all computers are, the majority of commercial, popular, grade computers are 64-bit. In the past, we had 32-bit, and you may still see reference to like 32-bit. Is your computer 32-bit or 64-bit? That's what they're referring to is the way that the digital information is stored into what are called processing words. And you can calculate the sound file size by this kind of mathematical formula. You have the sampling frequency. So let's say we have a song that is 3 minutes and 12 seconds long, and we want to record it, or it was recorded at CD quality, the compact disc quality, so at 44,100 hertz samples per second. And we have 192 seconds. That is 3 minutes and 12 seconds is 192 seconds. And we have a sampling depth of 16 bits, and we have stereo. So there's 2. We have to times it by 2 because there's 2 tracks, not just one. So that turns into this 270 million bits. That gets converted down into 32 megabytes to record a 3 minute and 12 second song or sound at CD quality. Here's some examples of different file formats that have timestamps. These are called timestamps, the numbers here. So these are milliseconds in this case. So at the very beginning of the interview at 0 milliseconds up to 2200 milliseconds, that is 2.2 seconds, we have an H sound. And then we have another H sound, and we have different sounds going on here. So that's the start timestamp and the end timestamp, and then what sound in phoneme representation. This looks like ARPABET maybe. ARPABET is a type of computer-friendly, well, more in the past than today, computer-friendly way of representing sounds. Here is from the switchboard corpus, which is a corpus of telephone conversations. You can see the start timestamp in seconds and the end timestamp between a conversation. And so we will see transcripts formatted like that. Typical audio file content. So you often have a header, which contains information about the sound file, and it may give information about encoding, and also byte order can differ across platforms. That is Windows computers versus Mac versus Linux. Okay, and some of the most common file formats dealing with speech processing are WAV. We'll see WAV a lot. You've probably already seen WAV in other classes or elsewhere. AIFF is Apple's kind of proprietary format, and there are other formats that you'll likely see in this class, that you will see in this class. So let's take a look here. If you actually open up a WAV sound, a WAV file, and look at it, like with an editor, like a text editor, you'll see these, you'll see all this information, all these little bytes that are stored. And this is actually the samples, like those, many samples. This is what is actually stored. So you'll see like RIFF here at the beginning of a WAV format, and then the chunk size, and then WAV here, and other information. And then if it's stereo, in each of these ovals, you'll see, two samples at that timestamp, left and right channels, and other information. So let's take a quick look here. If I grab a wave sample off of my hard drive, let's go to downloads here. So this is, let's see what this is.
My father has revealed the culprit's name.
It's a sample audio from, I think it's SpeechBrain. I pulled the SpeechBrain toolkit. And if I actually open this up, I'll just open it up in, let's try this. Yeah, so what I see here is I see RIFF at the beginning up there at the top left of my screen. And then I have some bytes here, and then I have wave format. Anyway, this is the actual representation of the sound in bytes. Okay. So yeah, it just looks like a bunch of garbly Greek to me type stuff. I don't know what FA, B9 means, but this is actually how the sound is stored on the computer. And then, an audio player like QuickTime or Audacity or, some of the audio player takes this garbly and turns it into an actual sound that we
My father has revealed the culprit's name.
So anyway, just want to show you that. Now, you don't need to know, what exactly all this means, but I just want you to be aware of the fact that that is actually how sounds are stored. Here's another header of a sphere. NIST is National Institute of Standards and Technology. Sphere header. Sphere is another audio format like wave. And so you can see here that the channel count is 1, so that's a mono. The sample count is 63,000 samples. Sample rate is 16 kilobytes or 16,000 samples per second. So that's what that is there. It's a header. Now, being able to convert between various formats, audio formats, is important. And these 3 up here are command line tools. SOX, Sound Exchange, and FM MPEG, and the NIST SPHERE tool, command line tool, can do a lot of conversion. So command line, this is what a command line is right here. I'm interacting with the computer with a terminal. If I type in FM MPEG, it'll give me a usage message which says, this is how you use this tool. Here are the options you can use with this tool to convert and do all sorts of stuff. That's what a command line tool is, and that scares you. Don't sweat it. We'll take it one day at a time with learning how to use a command line tools. SOX is another one. I think I still need to get that one on this computer. Yeah, I need to get that one. But those are 2 common command line tools to convert between sound formats as well. So like downsample or upsample, like increase, either decrease or increase the sampling rate and other things you can do with sounds with those tools. You can do a lot with Audacity, which is the purpose of Lab 1, right? Looking at Audacity, you can even find online converters of sound files online, just websites. And the cool thing is these are scriptable, so you can just write a little bit of computer code to do a mass conversion of a bunch of files if you need to do that. Okay. Yeah, so those are awesome. All right, so Lab 2, you'll look at PRAT, which is the most popular, I think the most popular speech visualization and manipulation tool that is used by linguists and probably other people. It is great for doing anything acoustic analysis, with acoustic analysis, and so that's the purpose of Lab 2, is to get familiar with that tool. If you already know it, great, you can learn more. I encourage you to continue to learn more. If you're new to PRAT, it'll be great. It's a great tool, and you will practice opening several different types of speech files and converting between various file formats and more analysis as well. So anyway, that brings us to an end of this little intro video for Lab, prep video for Lab 2. And kind of an overview of the course and some of the basics we'll see throughout the semester. So it's great to have you. See you next time.